This video, let's talk about hysteresis design in a comparator circuitry. This is based on a Texas Instrument presentation or live presentation I saw. And in general, it's a very good presentation, but it lacks some information about detailed calculations and also had a mistake. This slide basically show a design procedure for non-inverting input. So that means the input is here, come from the non-inverting side. The reference, the voltage you compare to, is come from the inverting side. I just do a little bit of recap about the hysteresis while we're doing that. So hysteresis basically is like we just take these design examples here. The reference voltage is 2.5 volts. And we intend to design a hysteresis 100 millivolts. So what hysteresis does, if you have a 2.5 volts reference voltage, and in the ideal case, you want to, whenever the input is above 2.5, and you will have a logic high, and below 2.5 volts, you will have a logic low. Output will be a low. The problem is the input could be very close to 2.5 and happen to be noisy like this, go up and down. And if this is the case, then this input voltage will go above, below these 2.5 volts multiple times, trigger some false alarm, produce whole bunch of false high or low output. One solution to this is we build hysteresis like this. We have a instead compared to one single 2.5 volts, we compare to two values. We call this V high, the higher threshold, and we have a V low, a lower threshold. Okay, how it works in this case, if this is 2.5 volts and the hysteresis is 100 millivolts, then we have 50 millivolts difference between here, and 50 millivolts between this middle to the lower side. Okay, that means this could be 2.55 volts level, and this lower will be 2.45 volts level. How this works is if a voltage, if the input is coming from a low to high, when the voltage increase above 2.5 volts, nothing happens, will stay low, output stay low. Only when the input voltage goes above this higher threshold, 2.55 volts, and you output the comparator outputs a high level. Same idea, if the voltage is dropping, when you're dropping below 2.5 volts, nothing happened until the voltage drops. Keep going below the lower threshold, 2.45 volts, then the output is switching to a low. Okay, that's the basic principle. Back to this circuitry here. And we can see how we choose these parameters. Say for example, in this case, the power rail is 5 volts, and the output max, because it's a logic signal high, will be close to the power rail, will be 5 volts. And the output mean, the logic low, normally you would not get very close to the ground, not get 0 volts, exactly 0 volts, you get 15 millivolts in this case. And the pull-up resistor is 20K because the output may be a floating output, so you need a pull-up. And first look, R1 is 100K, so R1 is the value over here, R1, because the reference voltage is 5 volts, so we need 2.5 volts reference. So R2 is very simple to choose. This one, just another 100K, so you have a voltage divider. It divides 5 volts into by 2, so get a 2.5 volts for the reference voltage. That's very straightforward. And you have R3, which is this input resistor here. And before we talk about R3, let's talk about the topology here. If you look at the topology, we have our input go through R3 and go to a feedback resistor and goes to the output. Okay, the major, if you are familiar with op-amp amplification circuitry, you know this is bad because the feedback is and to the non-inverting side, basically we have a positive feedback. If this is an amplification circuit, positive feedback can cause oscillations, all kinds of bad things that you try to avoid. But for a hysteresis design, use the op-amp here as a comparator, so that's what we really need. Okay. So let's talk about R3, the input resistor R3 here. R3, what we chose R3 here is the parallel resistance between R1 and R2. Why is that? That make a little bit difference because assume this op-amp, well, normally the comparator op-amp have a input bias current. That means it might have very little current flow inside the op-amp or flow outside the op-amp. If you have a certain current flowing on out, and if you choose this value R3 equals the equivalent value of this R1, R2, so whatever offset voltage you produced here and these nodes and here will be the same, so will not change your comparison. So that's why one way to choose this, we choose R3 equal to the parallel resistance R1, R2, which is 50K. So then a little bit tricky to choose R4, that's the feedback resistor. Okay, to understand the feedback resistor, choose R4. The circuit actually is quite simple, but we need to understand this, the output here. The output only can take two values. So it's output either 5 volts high or 0 volts low. Okay, if that's assumed for the case a input voltage goes from low to high, what happened here is because this is a low, so this will be low, output will be low, and the input voltage will keep increasing, and nothing will happen until the input voltage reaches 2.55 volts, which is a high threshold we are talking about here. Then at 2.55 volts, and this node will be 2.5 volts. Okay, that's exactly the same value at the threshold compared to this one. Then if you go a little bit above 2.55 volts, then this will go higher than that node. So this output will switch into high. So let's look at the critical situation, the critical input 2.5 volts, which is the VH here, the high threshold, and look at how this circuit is. That circuit actually is very straightforward. So we at the input we have a VH and 2.5 volts, and it goes through a resistor R3, then goes through resistor R4 here, and goes to the output. Okay, V output, and here will be the output, low output, so that's V output mean. So the small values, not quite 0 volts, like 50 millivolts in this case, just use that. And you notice this node is VREF. Okay, at this critical situation, just at the upper threshold, then this node will be 2.5 volts equal VREF. Okay, and if we look at another situation, if the voltage is going from high to low, then you will see very similar circuitry. We have V low. That means the low has to be an input and keep goes through R3, and goes R4, R3 here, and this should be V max, VO max. Okay. So this is still VREF. This is if the circuit is going from high to low, and nothing will happen until the input reaches 2.45 volts, the V low value at the input, and the middle point here will be the VREF. Okay, then from this two circuitry, we can make two equations out of this. Okay. And in this case, we know the current flow through R3 equal to R4, so the current flow over R3 is VH minus VREF divided by R3 equal to current flow over R4, that will be VREF minus V out mean divided by R4. Okay, and the same token, the second equation here, we have VL, the low threshold, minus VREF divided by R3 equals VREF minus Vmax, V out max divided by R4. Okay. And what we can do here is if we use equation 1 and 2, we use equation 1 subtract 2. Okay. Then the VREF canceled on this side. What's left over on this side here. So when we subtract all these equations, the denominator is same R3, and the numerator VH minus VREF subtract VL plus VREF, and VREF canceled. What's left over is VH minus VL. So we have VH minus VL divided by R3, and the other side, the VREF is cancelled, and we have minus V out mean minus plus V out max equals R4 here. So R4, we can rearrange this equation, make R4 equals what? R4 equals V out max subtract V out mean divide by V high minus V low. Okay. And remember, V high, if we look at the diagram here, V high and V low, V high minus V low, so that's the value of hysteresis. So this can R4 could be V out max minus V out mean equals V hysteresis. Okay, so this is R4. Now we look back this equation here. R4, this is R3. Did I miss R3 here? Yes, it should multiply R3 here. And R4 is R3 times V out max minus V out mean divided by V hysteresis minus 1. This is minus 1 should not be here. This is only if it's an inverting input, it will have a minus 1. It's not in this case. I think they had a mistake here. But the problem is you even have this mistake because the output max minus mean is about 5 volts, hysteresis is about 100 millivolts. So this division number is very large. Even you subtract 1, make very little difference. But in any case, if you solve this equation, you get R4 equals 2.43 mach ohm. Okay. So this is 2.3 mach ohm. Okay. Just to summarize this circuitry here. It's very simple, basically. The way to understand this is really it's a positive feedback circuitry, and essentially it's just a voltage divider. How do you choose this two value 50K 2.43 mega ohm? You choose these values whenever the input is upper limit 2.55 volts, and when its output 0 volts, and you get the 2.5 volts here. You can put this into the calculation to double check that. And in other ways, when the input is 2.5 volts, remember now the output changed. The output changed to the other side, to the top of the rail. So the output is 5 volts. then even if you have input 2.5 volts, output close to 5 volts, you still get the threshold 2.5 volts here. Okay, how do you set this up and downs here? It's just by use the voltage divider circuitry and the output, because the output is switching between 0 to 5, the low or high. So that's cause this change in threshold values. It's a pretty smart design. And I think that's all for this. And in the next video, we can talk about the configuration in the inverting input. Will be more interesting.